Okay, so as mentioned in the previous video, we're going to look at some meta-theorems. So these are theorems about logic, and we're going to look at some strengthening meta-theorems. So what do we mean by strengthening meta-theorems is that these theorems about logic are going to help us to strengthen our definition of theorem calculation. So essentially all that you want to get out of these meta-theorems and how we're going to apply them in logic is to add steps within our theorem calculation which allows us to, for example, write an absolute theorem at any step of a theorem calculation, and you would simply write the well-formed formula that is an absolute theorem, and in the annotation in the brackets beside it you would simply write absolute theorem. We will also be able to use any relative theorems that we prove, and these will be used as rules of inference. So the hypotheses of the relative theorems will become the numerator of the rule of inference we derive, and the denominator will be the conclusion. So to the definition of theorem calculation, we will add another step that says that we can write the conclusion of any relative theorem we have proven, so long as all of the hypotheses are written before. Okay, so that's essentially what you want to get out of this video, but now we're going to go through to justify and to state the meta-theorems that allow us to do this. So the first meta-theorem we're going to look at is called hypothesis strengthening, and even though it may look complicated, it's a very simple theorem. So it's A, and so the hypothesis strengthening says if gamma proves A, and gamma is a subset of delta, then also delta proves A. So what does this mean? So remember that gamma and delta are sets of well-formed formula, or collection of well-formed formula, which could be empty. And all it says that if we have a proof of A from the assumptions in gamma, and we take more assumptions, we can also prove A using the assumptions in delta. Right? So essentially, we simply don't need to use those extra assumptions that we have, and we get the same proof here. Similarly, if A is an absolute theorem, then adding any additional hypotheses will also make it a relative theorem. So, right, any absolute theorem is also a relative theorem. This is a weaker property than this. So by strengthening the hypotheses, we can still prove the theorem we need to prove. So hopefully that is straightforward. So all that this is saying is if we add more hypotheses, the theorem that we could prove before, we can still prove with more hypotheses. The theorem calculation never tells us that we have to use all of the hypotheses to prove it. Okay, so the second meta-theorem is stating that this proves operator is transitive. So, essentially, if gamma proves each of the well-formed formula B1, B2, Bn. So if we have gamma proofs of B1, B2, Bn using the hypotheses of gamma and any logical axioms, and in addition, each of those well-formed formula prove A, so B1, B2, Bn are hypotheses that we can use to write a proof of A, then essentially we can write a gamma proof of A, right? So being able to write a proof of A depends on the hypotheses. So here this tells us that we can restrict the number of hypotheses we need to prove a theorem A, provided that gamma proves each of the hypotheses that are required to prove the well-formed formula A. So what does a proof of this meta-theorem look like? So simply all it's telling us is that we can write each of the gamma proofs of B1, B2, Bn, list them as appropriate, right? So we simply write each step of the gamma theorem for B1, so B1 becomes a step within our gamma proof, and then from there we have written down hypothesis of gamma, or we can write new hypothesis of gamma. So we write the proof of B2 below B1, so B2 also is in our gamma proof, and so on. So we can write all proofs one on top of each other, so we get an extra long proof where B1, B2, Bn all appear. Then, since B1, B2, Bn are hypotheses in which we can prove A, we simply then use each of those hypotheses are written in our proof, so we then continue to write each of the steps of this proof of A, and A appears in our proof that we're constructing. And simply what's happening is we're only using hypotheses from gamma, because B1, B2, Bn are conclusions from gamma, and so the only hypotheses we're using to prove A are actually from gamma. So that tells us that the proofs operator is transitive. And then we can very easily see why it is that, for example, we don't have to write all of these proofs. We can simply use these results to prove the result that we want. So, the corollary of this, which then tells us that we can use any of the theorems, absolute or relative, to prove other statements, is stated in this way. So if we know that taking hypotheses in gamma and A proves B, but we also know that gamma proves A, then simply we don't need to have A as a hypothesis. We simply write a gamma proof of A and then use our proof of B here to write a gamma proof of B. So the proof of this essentially is this statement, which is why it's called a corollary, because it follows almost directly from this meta-theorem. But analyzing this result basically tells us that we can use this as a step in our theorem calculation. So just as I said before, we can use absolute theorems as steps within our proofs without actually repeating the proof within the theorem, right? So in the proof of this meta-theorem, we had to prove it by writing out each of these known proofs to construct our longer proof. So we're going to take a shortcut by using this corollary to say we can just take for granted that it can be proven and write it as a hypothesis. Or not as a hypothesis, but as a theorem. So this is a step, and we know that gamma proves B. So essentially, if we can do this, then we know this happens. And so here is a relative theorem. So we can use the relative theorems, or we can use absolute theorems to prove well-formed formula. So one more time, just to clarify what this means. So essentially what we're doing is whenever we want to prove B, and we know that A is either a relative theorem with the same hypothesis here, or an absolute theorem, it says if we take this sort of as a hypothesis, but we're going to state it as a relative theorem or absolute theorem in our assumptions, and we prove B, then it simply means that we didn't have to worry about that in the first place. So hopefully that is clear. Of course, if you have any questions, do post them onto Moodle and we can address it more clearly in class and look at examples to see how this applies.